we talk about the scheduling for various different scenarios. In a batch system, we talk about the various different scheduling algorithm. The simplest one is called first come, first serve. Okay, or it's called first in, first out. So it's we call it Fifo. And then we find out Fifo has some kind of problem, because if you have a process with a very long CPU time, CPU burst, arrives first, and then a process with a very short CPU burst arrive next. So the short process has to wait for the long process to finish. This is called some kind of inefficiency. So Fifo is the simplest algorithm, but it's not the most efficient one. So then next one we talk about is called the first shortest job first. Okay, so that means if I have two processes waiting for the CPU, the scheduler can actually pick the process with the short CPU burst first, and then pick the CPU with a longer CPU burst next. So that's called the shortest job first. And then the last one we mentioned about is called SRT. It is called shortest remaining time first. Okay, so in that case, now the difference is that suppose that we have a process. We have process, okay, process 1, process 2, process 3. So the arrival time for the process is process 1, 0, process 2 is probably 2, process 3 is probably 4, and the CPU time, the burst time is let's see, 40, 20, and 10. Okay, so in that case, so for the Fifo, you will find out, at the time 0, when process 1 arrives, so the process 1 gonna take the CPU, okay, and run for 40 time unit. And then even though process 2 arrives at the time 2, right? This is time 0. So process 2 arrives. But the process 1 is taking the CPU. So process 2 has to wait. And when process 3 arrives at the time 4, process 3 is still also gonna wait. Okay. So until process 1 complete the job at the time 40. And then now we have two processes actually in the process list, right? In the ready list. So these are process 2 and process 3. Okay. Now who's gonna actually take the CPU next? Based on the Fifo, process 2 gonna take the CPU, right? Even though process 2 has a longer CPU time, but the process 2 arrives before process 3. So based on the Fifo, the process 2 take the CPU, and the process 2 gonna run for 20 time unit. So from 40, run for 20 time unit, then process 2 finish at the time 60. And then process 3, you're gonna take 10 time units and complete the job. So all the process gonna complete the job at the time 70, and the process 1 actually finish first. Now the second approach is called shortest job first. So when process 1 arrives at the time 0, process 1 is the only process in the ready queue. So the process 1 gonna take the CPU. Okay. Now when process 2 arrives at the time 2, and the process 3 arrives at the time 4, they cannot start because process 1 is in the CPU. Okay. And then when process 1 finishes, so there are 2 processes in the ready queue, okay, in the ready list. So then process 2 and process 3, and then the scheduler going to decide who's going to be the next one, and then who's going to be next one. So the scheduler going to check which one has a short CPU time. So then process 3 is 10, process 2 is 20. So process 3 going to take the CPU and finish the job at time 50. And then process 2 pick up the 70. That's called shortest job first. Now, shortest job first, we find out when we calculate the total CPU time, the average is actually CPU time. We find out shortest job first is much better than the first come, first serve. Okay. The last case is the shortest remaining time first. So the shortest remaining time first is a kind of preemptive scheduling. Now, talk about a preventive, FIFO and the shortest job first. These are non-preemptive, okay? Okay, these are non-preemptive. So that means if a process is one process is currently in the CPU, is running, so no other process can kick the process out, even though the other process has a higher priority, like the shortest job first case. Even though a process 1 has a very big CPU time, long CPU time, and process 1 is currently in the CPU, and process 2 or 3 has a short CPU time, but process 2 or 3 still cannot run because process 1 is in the CPU. Since it's non-preemptive, so you cannot take the process out. Now the shortest remaining time first is different. It's a preemptive, okay, which means that the process currently waiting for CPU can kick the process in the CPU out, okay, depend on the situation. So let's take a look at the SRT. So let's see, process 1 arrives at the time 0, right? So process 1 start to execute. And then at the time 2, process 2 arrives, okay? So now in this case, the shortest remaining time, remember, it's a preemptive. So now you have process 1, which is currently in the CPU, and the process 2, which is waiting for the CPU. And then we need to figure out who's going to actually take the CPU. So in this case, we need to build a table. So at the time 0, process 1 arrives, and the process 1 has a CPU time 40. So the process 1 going to has a 40 CPU time, okay, at the time 0 before it starts. And the other process are not available at this time. Now at the time 2, things have been changed. Now what's the remaining time for process 1 at the time 2?
38.
38, because process 2 has been executed for 2 time units. And the process 2 arrives, and based on the table, it says process 2 need 20 time units for the CPU. And the process 3 is still not available. So in that case, process 2, oh, I'm sorry, 38, yeah, process 2 will be selected. Now, in this first case, process 1 is selected because it's the only process. So process 2 is selected. So the process 2 going to take the CPU.
Professor, just a quick question. What would happen if process 2 took 38 time units and so both P1 and P2 had 38 left? Would it continue with process 1 or would it?
That's a good question. It basically depends on the scheduling.
Okay.
Some of the scheduling going to actually, if you have two processes with the same CPU time, they're going to randomly pick a one. So if it's in the certain circumstances that if P1 is unlucky, it will be actually kicked out and replaced by process 2. And it still could be P1 because P1, P2 has the same CPU time, right? So the other approach is, if you have two actual processes with the same priority or same CPU time, then it's based on the Fifo between these two, who actually arrived first. Now, in that case, of course, P1 arrived first. So P1 going to continue. Even P2 has the same CPU time. Yeah. It basically depends on the design of the scheduler. Any other questions? So normally we think that if P1 and P2 both has the same CPU time, and P1 should continue, right? Otherwise, you're going to cause some kind of context switching, which is kind of bad. But the reality is depend on this design of the scheduler. Okay, so P2 takes the CPU, and then at the time 4, P3 arrives, right? So when P3 arrives at the time 4, now, so P1 still has 38 time units remaining, and P2 now have 18, right? And the P3 has time 10, okay? Because based on the paperwork, based on the table, P3 has a 10 CPU time. So P3 going to be the shortest. P3 has the shortest remaining time, okay? So then at the time 4, P3 take over, okay? And they're going to run for 10 time units. It starts from 4, so it's going to end at the 10, 14, right? So then at the time 14, this is still 38. This is still 18. And this is going to be done, finished. So now we're going to pick the P1 and P2. So now P2 can be selected, right? So P2 going to continue. It continue to run 18 time units. So 14 plus 18, that's 32. So P2. Yeah. So then at the time 32, this is done. Okay, this is also done. And then 38 remaining. So, and this is the only one. P1 is the only one in the ready list. So then P1 gonna run for 38 time units. So that's gonna be 70. So P1. Okay. So after 70, all these process just complete. Okay. So that's the shortest remaining time first. Okay. So now, which one is the worst? Which one is the best? Okay. Then you can easily figure out, by calculate the CPU time. So we find out that you basically need to check that what's the average CPU time for each of the scheduling algorithm, right? The average. So for in order to calculate the average, we need to calculate each individual process. What's the CPU time for each individual process? So in that case, you will find out, the FIFO for P1. So P1 gonna take, okay, I'm running out of space here. Let's say for FIFO. Now the P1, the CPU time for P1 gonna be, P1 actually take a total of 40, right? From the start of the P1 to the end of the P1, it's a 40. Now P2, P2 actually end at 60, okay. But P2 start at the 2, right? So it's a 60 minus 2, so it's a 58. And the P3 gonna be 70, but it starts from 4, so it's actually 66. Okay, so that's actually the total CPU time each process gonna actually, use. So it's from the start to the completion. Now, shortest job first. P1 is 40, right? No change. Now P2 and the P3 actually is switched. So actually P3 actually finished at the time 50, but P3 started at 4. So that means it's just 46. Now P2 finished at the 70, but it started at the 2. So it's a 64. Or 68, I'm sorry. Now, what's the shortest remaining time? P1 start at 0, but it completed at 70. So P1A is the longest, even though it's the first one to start. But because P1 is so long, so it completed the last. And the P2's end at the 32, start at the 2, right? So it's 30. Yeah, you have to stop me if you actually not sure what I'm doing. So for P3 actually finished at the 14, but it start at the 4. So it's actually 14 minus 4, so it's 10. Do you have any questions on this? So that's the CPU time for each process, for each of the scheduling algorithms. Now, what's the average? So let's take a look at the average, okay? So the average time for FIFO, let's check. Okay, I need a calculate. Let's just check. Okay, I find a calculator now. So let's do this. Just a very simple job. So for FIFO, I'm talking about a 14 plus 55 or 58 plus 66, right? Equals 164. Because we're talking about the average actually CPU time, so we're going to divide by 3. So it's a 54, okay? So the average CPU time is 54 for Fifo. Now let's take a look at the shortest job first, okay? The shortest job first, let me actually clean up. It's a 40 for process 1 plus 68 for process 2 and 46 for process 3 divided by 3, 51. A small improvement, right? Now, can you figure out why the improvement is so small? Now let's take a look at the further case. Shortest remaining time. So we have a 70 for process 1 plus 30 for process 2 plus 10 for process 3. That's 110 divided by 3. 36. So for Fifo, it's 54, the average. Shortest job first, it's 51. And the shortest remaining time, it's 36. So certainly this is the winner. This is a loser. And shortest job first, it's in between. But now it's not really that a big improvement, right? So can you tell me why in this case? Okay, let me explain this. Even though the shortest job first is supposed to pick the process with the short CPU time first. However, in this particular case, even though P1 has a long CPU time, it's much longer than the remaining two. However, P1 still actually arrive first and execute first. Remember, shortest job first is not preemptive. So that's the reason why the process 1 still takes most of the CPU time first. Force the P2 and P3 wait for a longer time. So that's why the improvement is not really that big. It's just actually between P3 and P2. So you swapped. So so in that case, P2 actually, wait a little longer. P3 actually, wait a smaller time. So the idea for the shortest job first is we have to make sure that the process with shortest CPU time should wait less. Okay, so that's basically the idea. Because if the shortest job actually wait less and complete first, then in terms of average, the waiting time is relatively small. Okay, so that's the reason why the shortest remaining time first is the best in this case. Now, the actual case is more complicated. Now, even though we say SRT is the best algorithm, however, we actually did not count the context switching time, right? So we assume that if you switch from P1, P2, P2, the context switching time is it's 0. We make that assumption. So that's the reason why when we calculate the time, we did not count the context switching time. But for the SRT, certainly there are more context switching than the other cases. So if the context switching time count, then the improvement is not really that big, but it's still a big improvement. It's probably not 36, but if we actually think about more context switches that are involved, then the improvement is probably going to be less than what we see in the paperwork. Okay. Okay. Any questions before I move forward? So this is the shortest, remaining time. Okay. So now let's talk about performance. So that's something we just did last time. Okay. So that's the other example, and we find out that the average time for Fifo is 7.33. Average time for shortest job first is 7, and the shortest remaining time first is 5.66. So still at the best. Okay. Now let's talk about this in general. When we talk about how to estimate the total CPU time for each of the scheduling algorithm, so the one we just talked about it, we just talk about just one run. But in reality, for each process, once the process start, it may actually take a CPU time. Say, okay, here's the CPU time I take, and then it's done its job, right? And then the process is going to be actually moved to the ready list again, and then when it's time again for the process to actually execute, then you're going to take another CPU time. So this is each of these is CPU burst, okay, and then a CPU burst, and then a CPU burst, okay. For each process, it's going to be like this, okay. So when we talk about this, when you talk about the CPU time, so here it's probably going to take a time millisecond, and this code probably going to be 9 milliseconds. This is probably going to be 6, and this is probably going to be 4. So each time the CPU burst going to be different. Okay. Now how can we estimate the total CPU time? Okay. Now for long time scheduler, it's relatively easy because the total CPU time is measured between the process creation and the process destruction. So what's the total CPU time? Okay, here's the starting point for the process. And after the process actually finished the 4th CPU burst, and the process just finished the job, and it just quit. So from the creation to the destruction of the process, that's the total CPU time. That's for the long-term scheduling. But the long-term scheduling only measures the overall CPU time. Okay, from the creation to destruction. Now the overall CPU time, if you actually start the same program, for example, you every time when you start to run this computer game, and you double click the icon, and the program just starts, and the process actually start to run, and then once you finish the game, it just terminate, and you can measure the total CPU time. Okay, and next time when you start the game again, and then you finish the game, and then you measure CPU time, the total CPU time might be different from each case, each time from when you actually play a different game. That could be different. Okay. So, however, one good thing about the computer actually program is, so each of the application, each of the programs has its own characteristics. Okay. So which means if the program, the CPU time, total CPU time for this particular program is about 100 millisecond, for example, or 100 second. So whatever the CPU time you measured in the past. So most likely, that's probably the average actual total CPU time. Okay, so it's unlikely that if you actually run the same program, and this time it takes like 100, and the other time it takes 5 seconds, and another time it takes 6 seconds, and then another time it takes 200 seconds. Okay, so that's unlikely case, because for each of the computer application, they have some sort of characteristics. Okay, so that means if you actually measure the history of the performance of a process, you can use the history to predict the future, because they're going to have the same characteristics. For example, when you talk about some of the application, like scientific computing software, so most likely they're going to take the CPU time, and most likely they're going to take the same amount of CPU time. Okay, so it's unlikely that this time they could take 1 second, the other time they take 100. It's not really predictable. That's not the case. Now, for another example, like if you use a social media software, like you use chatting, with other people. Now, these kind of softwares are basically bursty in natural. So it's kind of like you have a very short burst when you actually send a message out, and then it will be silent for a long time, and then there's another burst, okay, and then another silent. So this is basically the characteristic of this particular program. Okay, so to measure the total CPU time, it sounds like it's an impossible job to do, because how can I figure out what the CPU time it will be before I start to run the program, right? How can I tell you that even before I start the program, how can I tell I can need like 10 seconds or 20 seconds? Sounds like that's impossible, right? Before, how can I predict? Now, technically, you can actually do this by look at the history of this program, and then you can predict, say, I expect that this program going to take 10 minutes, because historically, it always, took 10 minutes. Okay, so that's the reason why in most cases, we always use the history to measure the process CPU time. Now, for short term, then we need to measure each burst. Okay, the total CPU time, the CPU burst, changes from each arrival and the departure time. So here it's arrival time, and here's the departure time. And then there's a silence, and arrival time again, departure time again. So it's arrival time, departure time, arrival time, departure time. So they're different. Okay, each time it's different. And now, if I complete this CPU burst, it's arrival time, departure time, I measure it. Oh, it's a 10 time units. And then when the next time actually the CPU actually start to burst for this process, how much time should I predict? And most likely we can actually, if we use the history, we're going to predict that, okay, it will probably take 10 minutes, 10 time units, because, it did, previously. So how can I actually predict this? Now that's very important, because if we use Fifo, first in, first out, that's not important. But if we use the shortest job first, now that's really important. That matters. Why? Because if you have, for example, 3 processes, process 1, process 2, process 3. Okay, so now all 3 processes are in the ready queue, waiting a fight for the CPU. And the scheduler I use is shortest job first, right? Now with the shortest job first, now I'm gonna pick which one I'm gonna pick. Okay, now whether I'm gonna pick a P1 or P2, P3, I need to figure out which one gonna has the shortest CPU burst, right? And now, but how should I know which one has the shortest CPU burst? And then I look at the past. For example, if for process 1, the CPU burst is like this. And then at this moment, the scheduler is kicking in to pick the next CPU. Okay, now process 2 has this kind of CPU burst. And it's process 3, like this. Okay, now it's a time to pick a P1, P2, P3. Now, what do you think? Which one you're going to pick? If all 3 actual processes is fighting for the CPU at this particular moment.
Would you pick P2?
P2, right? So sounds like a P2 should have a short CPU burst, even though we don't know, because you have to start to run the P2 yet, so we don't know what it is. But based on history, we find out P2 tends to have a short CPU burst. So we're gonna pick a P2 based on the shortest Java first. Okay, so that's basically the idea for using the short-term scheduling algorithm. Now, in more generally, the most common approach use exponential average. So if you have a cup of history here, so we're going to actually use the average of this history to predict the next CPU burst. Okay, and not just this, they use the average of they also use the average of the previous predicted CPU burst. Okay, and plus the average of previous observed total CPU. Now, observed total CPU is basically the actual CPU that we actually used. So to predict the previous next CPU burst, we use the previous predicted CPU and the previous actual CPU CPU burst. And then here we put a particular number alpha. Alpha is used to control the relative weight of the last observed CPU burst and the predicted CPU burst. So the value of alpha is between 1 and 0. Okay. So so for example, if I pick alpha equals 1/2, so then the predicted CPU burst is, let me actually do this. All right, let me erase that one. So if alpha is 1/2, then the next predicted CPU burst is 1/2 the previous actual CPU burst plus 1 minus 1/2. It's also 1/2, right? The previous predicted CPU burst. So I use the average of previous actual CPU burst and the previous predicted CPU burst, and use this to predict the next one. Okay, so that's what I do. Okay, but if you actually put more weight on the observed CPU CPU burst, then you can put you choose the alpha that close to 1. Okay, now if alpha is a 1, then the predicted CPU burst is the same as the previous observed CPU burst. So So if alpha equals 1, then Sn plus 1 equals T1, Tn, right? So the previous actual CPU burst is used to predict the next one. Now, if alpha equals 0, so that means Sn plus 1 equals Sn. So that means I keep use the same predicted value. I don't actually, I ignore the previous actual CPU burst. So that's basically used in the shortest job first. Okay, or the shortest remaining job first. Okay, so this is, so, you know, the truth is, we don't know, when all the processes are actually waiting in the ready queue. When the scheduler, the shortest job first scheduler, try to pick one of the process, we don't know actually which one has the shortest actually, CPU burst, because you haven't started the process yet, right? So that's why we use this formula to calculate the predicted CPU burst. And whoever has the shortest predicted CPU burst will get the CPU. Okay, that's basically how the scheduler going to use to calculate the total CPU time. It's not really the actual CPU time, because we don't know which one has the shortest CPU burst yet, So that's why we use predicted CPU burst time. Okay, so in 3.3, we're going to talk about a scheduling algorithm for some kind of interactive processes. So interactive processes must, it's kind of process like it can actually interact with the computer more frequently. It's just like a social media software. So they are very actually interactive, So, if you have a multiple processes with both these processes are interactive, so they're gonna actually, they're gonna take the CPU back and forth in turn. Okay. Now for interactive process, the widely used scheduling algorithm is called round robin. It's called round robin. Okay. So first, interactive actual process must use the preemptive scheduling, because you want to actually, the scheduler want to actually schedule each of the processes actually in turn. So the scheduler want to actually allocate the CPU time for process 1, and after process 1 takes the CPU time for a certain period of time, the scheduler going to take the process 1 out and allocate the process 2, and then after a certain period of time, and the scheduler going to actually remove this process 2 again and put another process 3. So in that case, this kind of algorithm is called actually round-robin scheduling algorithm. Okay. Now, in the round-robin algorithm, so a time quantum, normally we use a letter Q to actually, so we're going to allocate the time quantum for each of the process. So every time when the process actually take the CPU, then the scheduler is going to guarantee that this process will be in the CPU for no more than 1 time quantum. Okay, so time quantum is a small amount of time. So it's typically like a 10 to 100 milliseconds, during which a process is allowed to use the CPU. So that means every 10 to 100 milliseconds, then the scheduler going to actually switch a process. So each process only allows to stay in the CPU for 10 to 100 milliseconds. Okay. So the round robin uses a single queue of processes. Okay. So that means there's only one, like a ready list. So then they have a process 1, process 2, process 3. They're waiting in the queue. Process 4, waiting in the queue. Okay. When the time's up, then the current process will kick out. And next process at the beginning of the queue will be selected. And then after timeout, this process will kick it out and put it in the back of the queue. And the next process is gonna be running. And this process is finished and put in the back of the queue, and the next process is gonna start to run. So it's gonna continue to actually move back and forth among the processes. So the process at the head of the queue has the highest priority and is allowed to run for queue time units. When queue ends, the process is moved to the tail of the queue, and the next process now at the head of the queue is allowed to run for the queue time units. Okay. So it's basically take turn. Now here's the typical scenario for the round robin scheduling algorithm. Okay. Now suppose I have 3 processes, 1, 2, 3, and the total CPU time is 4. Okay, 4. And for process 3, the total CPU time is 2. That 4 could be 4 milliseconds or 4 seconds. It doesn't matter. Just some time unit. And the time quantum allocated is 1. So that means in the round robin, if I have a scheduler, so the scheduler actually gonna check each of the process. So process 1, okay, it's in the CPU, it's in the head of the CPU. Okay, that's a tail. So you're gonna pick a process 1. So the process 1 gonna actually up and running. Now remember the time quantum is 1, right? So we actually only run for 1 time unit. And then the process 1 gonna be put in the tail. So the process 2 gonna be moved forward. Process 2 move forward, and process 1 gonna be put in tail. Put in the tail. Okay. And then the process 2 actually start to run. Once the process run for 1 time quantum, it finish at 2, and the process 2 gonna be actually moved to the tail. So now it's process 2 in the tail, and the process 1 just move forward, and process 3 gonna be at the head. So next one gonna be process 3. And then another round. Then another round. So now, because process 1 actually requires 4 time units, so process actually 3 requires 2 time units. So after 2 rounds, process 3 finish the job, and the process 1 and 2, has to run for 4 rounds and then finish. So process 1 initially gets the CPU every 3 time units. So at the time 0, it got the CPU, and at the time 3, it got CPU, because time 1 and time 2, it's run by the other process. Okay, and again, it's run by this. When process 3 actually quit the job, and the process 3 done its job, now it's only actually between process 1 and process 2. Now it's more frequent, because then every 2 time units, the process is going to actually get the CPU. So this is longer, waiting time is longer, right? But now it's shorter, because three actually quit out of the competition. So that's the round robin scheduling algorithm. Okay. Now for this, to calculate the CPU time for each process, it's very straightforward, right? For process 1, start from 0 and end at 9. So process 1 gonna equals 9. Process 2, we assume it's also start from 0 and end at 10. So process 2 equals 10. And the process 3 equals 6. It's end at 6. So you can actually see, even though, round robin just run actually these processes back and forth. And if a process is shorter, then there's still a chance that the process is going to finish earlier, like a process 3. Even though process 3 actually get the CPU time the last, but it's finished first because no one can take the CPU for as long as they want. So everyone just take a turn. So eventually, process with a short CPU cycle going to actually finish earlier than the process with a long CPU cycle. Okay. That's called a round robin. And round robin is actually widely used by most of the modern computer system. So if you have, 20 or even 100 processes running on the same computer system, if we use round robin, then the CPU going to actually take a turn to run each of the process. Okay, so that's round robin. Now the next scheduling algorithm we can talk about is called multi-level scheduling. Okay, now multi-level scheduling maintain a different process queue. Okay, so it actually maintains a separate queue of processes at each priority level. So now in multi-level scheduling, processes in the computer system are prioritized. So some of the process has a higher priority than the other processes, and which is true, right? For example, if you some of the processes running actually in the kernel and doing some important, job, and some applications like a computer game, they're just application. So if you have two processes, actually, the processes running the game compete the CPU with processes running like a security checking. So what do you want? You want the process with security checking to get the CPU, right? So that means the security checking process has a higher priority than the process that running the game. Okay. So in that case, the higher priority process gets the CPU first. So in that case, now you have a multi-level scheduling. So that means I create a couple of queues. Okay. Okay, so that's called a level, let's say level 5. And that's level 4, level 3, and then level 2, level 1. Now when each process is coming, created, then the operating system is going to allocate a priority to the process. If this is an important process, then I threw this process into the level 5 queue. And then another process 2, I put in level 4 queue. And process 3, I've also put the level 4 queue. Okay. And process 4, I put in level 3 queue. So that's the lowest level queue. So now multi-level scheduling basically maintains process in queue are at the n different priority level. In that case, n equals 5, right? So 1, 2, 3, 4, 5. The process at the head of the highest priority queue is selected for execution. Okay, so let's say I have process 1, process 5, process 6, process 10. I have process 2 and 3 and 7, and process 4 and process 9. So then each level there's a queue. So this is the head of the queue, and this is the head of the queue. This is a header. Then we'll have more processes actually in lower level queue. Now the operating system scheduler going to check the highest priority level, and it will pick the process 1, which is at the header of the highest level queue, and then I can execute process 1. Once process 1 finishes the job, and then I pick process 2 or process 5 and process 6 and process 10. So if there are any process in the highest level queue, then I'll always run the process in that level of queue, in that level, in the queue of that level, until the level 5 is empty. And then the scheduler going to check the next level queue and run the header of the process, and then the next one, the next one. So the process at the head of the highest priority queue is selected for execution. When the maximum time allowable for this level expires, the running process moves to the tail of the same queue, and the next process starting using the CPU. So as far as their process in the highest level, and the round robin going to run in this level. The next level, they have to wait. Okay. Now, if a new process with a priority higher than the current running process, then you have to preempt the running process. Okay. Now let's say, suppose I have in the highest level, all the processes are completed. So this process, this queue, this level of queue is empty. And then the operating system scheduler gonna check, the next queue and start to execute the process in here. So currently, process, let's see, what's that number? Process 3. So process 3 is selected and it's running. And suddenly, a new process is coming, process 11, and the process 1 is actually placed in the level 5 queue. And then this process will be preempted and free up the room for process 1. So process 11 for process 11. So process 11 going to take over the process 3 because process 11 is in the higher level queue. Okay, which is actually currently picked. Okay, so the process at the given level can run only if all queues at the higher level are empty. So example is S will run only, after a process at level n and n minus 1 terminate. So that's the example in the Zybook. So don't read that one. So that's not the one we talk. Now let's take a look at the example. So here's the multi-level scheduling, and I have a highest priority queue n, and then next one n minus 1, n minus 2, all the way to 1. So now currently there's no process in the level n, right? So then we're going to check the next level, and then process actually R looks like a process R is at the header. So process R going to actually, oh no, process Q is currently running. So if process Q at this level finish the job, process Q going to be placed after the, at the tail of the queue, and the process R going to actually take over. Okay, so then you have a Q and a P in the queue. And then when process R finish the job, put in the back, and the process P going to be actually up and run. And during the execution of process at the level n-1, if suddenly one of the processes coming, okay, I call it A, and then it will actually preempt the current process and let the A to use the process. Okay. Excuse me. Any questions? Okay, the last one we're going to talk about is the multi-level scheduling algorithm. It's called a multi-level feedback. Multi-level feedback. Multi-level feedback scheduling is very similar to multi-level. However, the multi-level feedback, allows all the process, a newly arrived process, to enter the highest priority queue and allow to run for queue time units. So each actually level use the round robin. Now, when process actually executed for one queue time unit and it's still not finished yet, then this process is going to move to the next level, the lower priority level. So when queue exceeded, the process is moved to the next lower level queue, n-1, and is allowed to run for 2 queue time units. Okay, so multi-level feedback algorithm, it works like this. So the high priority queue is n, level n, and here's the CPU. So when a new process arrives, new process placed in the queue over here. Now the time quantum is Q. Now, if the process actually executed after Q time unit, still not finished yet, the process gonna be placed in the next level Q, n-Q, and the time quantum for this level of is 2Q. It's double the time quantum. And then if it's still not finished, you're gonna move down to n-2, and the time quantum is 4Q. Okay. So a process arrive at the highest level. They take the CPU and run at the CPU and not finish yet. And then you're going to put down to the next level CPU process, next level queue. Okay. And then when this process is going to continue to run, depend on whether there's any new incoming process which takes the highest level queue. If the highest level queue is empty, and then this process may get a chance to run again using round robin with the time quantum 2Q. So each time the time quantum doubles. Okay, it's just keep going down. Now, multi-level feedback queue automatically favors the short running process, because if it's a short running, then most likely they're gonna finish in a high priority queue. Not if it's not n, then you're gonna finish in n-1 or n-2. But if it's a process that takes a long CPU time, then in the first actually high priority queue only actually run for the queue time unit, and then run for 2 queue time units, and then run for 4 queue time units. So each time when you run next, it's going down to the next level. Okay, so this basically means if the process has a long CPU time, most likely it will eventually going to be put in the low level queue, right? Now, if the process is very short, most likely it's going to be completed in the high level queue. If it's not n, but it's going to be n-1. So it will be very quickly finished. So this this is a good approach. It's called a multi-level feedback queue.
So, Professor,
Yes.
do all processes for this start in the highest level and then just move their way down depending on how much time they're taking?
That's the plan. Yes.
Okay.
Yeah, that's the plan. Now, when I say this, yes, that's true. But also, you should realize that in some of the operating system, they use a multi-level queue for like all the user process. You know, for the kernel process, sometimes they always has a high priority. You know, they're never gonna load their priority never gonna load down. But for most of the process, like in the user level, they use the multi-level feedback. So they treat all the user created process the same. Initially the same priority, and then go down, and it's more or less like a short. If you have a short process, then it will be finished quickly, and if you have a long CPU burst, then you're gonna finish. Eventually, you're gonna be actually positioned in the lower level queue and still waiting for the CPU, right? Once you actually put it in the lower level, then you have to wait for all the process at the high level to complete. So, yeah. So this is actually the multi-level scheduling algorithm. So each one using the round robin. Okay, but as the actual level becomes lower and lower, the priority is lower and lower, and the time quantum becomes bigger and bigger. Okay, each time the time quantum doubles. Okay, so that's basically the idea. Okay. Now, what's the performance? Now, the performance, it's a little bit more complicated to measure, but it's still actually doable. So the response time of a process is elapsed time from the submission of the request until the response begin to arrive. Okay, so in that case, the response time is pretty quick. So once you submit the process, it's always put in a high priority, so it will be treated very quickly. But the completed time, that the whole CPU time may not be that long, may not be that short, because it depends on the total CPU time for the process. Okay. So in general, the interactive scheduling algorithm favors the short process. Whether it's a round robin or feedback or multi-level or multi-level feedback, all these basically favors the short process. If the process is short, then they tend to finish earlier. If the process is long, they tend to actually finish, takes longer time to finish. Like a round robin, right? Because it can actually switch back and forth. So the short actually process tends to have a short cycle, you know. Now the performance of the time sharing, like a round robin, it basically depends on a couple of different facts. The performance depends on a couple of different facts. One, okay, I think we're running out of time. Okay, so I'm gonna stop. So let me stop at the performance time for the interactive process. So for the time sharing. Now you can actually, the performances depend on one, the time quantum. Other thing it's related is the context switching. Okay. Now why I mentioned context switching? Because the time sharing, the round robin, it can frequently doing the context switching. And the running time, the time quantum tends to be very small, like 10 milliseconds to 100 milliseconds. It tends to be small. And if the context switching is relatively big compared with the time quantum, then you cannot ignore the context switching. Because one, it can actually frequently do the context switching. So if you accumulate all this context switch time, you cannot ignore it. So the context switch time is also important. And also the number of processes. So the more processes actually fighting for the CPU, the performance is going to be slower. So we're going to talk about this later using this particular example. So I'm going to post this the presentation on the Blackboard. So, but I encourage you to actually run the Zybook. The Zybook gives you a lot of ammunition, which is pretty good, you know. So here I only give you the diagram, but the Zybook gave you a lot of ammunition, so you can actually feel and how this tie sharing, actually how this round robin works. It's pretty cool. So I think that's pretty much all for today. Do you have any questions before I leave? Okay, I think that's pretty much all for today. Let me turn off the time, stop the recording.